So for daylighting, the goal here is to inform design. I take the approach from an analysis standpoint that validation is bad because you're too little too late. If all you're doing as a consultant or as an engineer, how many engineers do we have in the room? All right, one. For those watching, we had one lonely hand. But even if you're an architect and you're trying to bring information into a design, if you're analyzing a design, you've already made the design decisions. You've already designed it. And that's sort of a slow process. And in real life, we end up running out of time, falling in love with the original design, right? There's a lot of things that can go on. And I've found from a daylighting perspective, we often come in with too late to really alter the design in a meaningful way. So we in Smith Group tend not to like to simply validate a few design options. We challenge ourselves to try to deliver analysis in a way that actually informs the design decisions, ideally as they're being made. So as you go one direction, you can understand why. Or rather, here's an example. Most analysis tells you how you're doing. So I can say, you're doing badly. And you're like, oh, okay. Well, what can I do better? I'm like, well, now I'm just guessing because my analysis just told you you're doing bad. It doesn't say anything about how to improve or what you should or could do. I then immediately start relying on my past experience. That's garbage. We've got to challenge that. We can do a lot better. And let's say based on past experience, I say, okay, you're doing badly, so here's my solution. It's going to ruin your design. You're going to say, no, unacceptable. What else? And here we are in this horse trading thing where we've forgotten the analysis completely, and we're all going based on rules of thumb. So what we're showing here are methods to leverage data and leverage parametric analysis to inform that design decision. So we're not going off experience or rules of thumb, but we're going off of actually measured simulated data because we can afford to do this in ways that were never before possible. So let's look into what that means. This is traditional analysis. We have full floor plate calcs, takes an hour to run, depends on your calc level quality. If it's got a complex facade, this is what we built in the previous session. I say, okay, that's cool. It's not good enough, right? Which is pretty much what we always end up finding out. Not quite good enough. Now, there's some things I can learn from this, but recognize if I were to look at this, well, okay, I notice maybe in this section here, I want more red. Let's just assume for discussion that red is good, blue is bad. I want more light in here. Well, which of my many design decisions caused it to not be good enough? Was it the window to wall ratio, like the total amount of glass? Was it the fin depth? Was it the fin spacing? Was it the fin rotation? Right? These are all decisions that we made. And if you think about that parametric script, those are all decisions we have control over. Decisions I want to, as a consultant now, decisions I want to inform. Even having done a lot of designs, I honestly can't tell you which one is more important or how important it is. But that's important to the designer to know. So which of those decisions matters most and how much and why? So rather, that's what we wanted to answer, because we wanted to be able to explain that not based on a gut feeling, but with some data. So what we did, this is getting into design space thinking, where rather than analyze that facade, because there are so many different combinations, right? Every gradient could be tweaked slightly. We broke it down into its constituent parts, and we built a simplified version of that facade that looked at those major decisions. So we iterated every possible window to wall ratio, every fin to depth spacing ratio, fin rotations, and even the window VLT, because we know those are the four things that really mattered. So these are the constituent parts. And as you see in some of these examples, one parametric model could be any of these facades. And any of these facades could be found potentially in our design. We're not sure which ones, because we don't know what the designer is going to do yet. Again, we don't want to react to a design that's already been made. We want to simulate every possibility that they might come up with. So we did exactly that by breaking it down into these smaller parts that we could then learn from. And what you end up getting is this, now we're getting to data analytics. So all plotted out. Let's see if we have time to go through this. The first question we often have is, well, what's optimal? Again, this is a presentation about my opinions, so take this with a grain of salt, but I think optimal is bullshit in our industry. I think we rarely, honestly, have cases where we're truly optimizing. I think in the realm of design, it's more a matter of better or best, and you get to make your case. Now, metrics matter, but as we'll see here, if we were to ask the question, what is optimal? Well, best is shown in that gold star in the lower right-hand corner. So a quick review here. That's daylight autonomy on the right, so the higher the number, the more daylight you have. And then on the y-axis, on the left-hand graph, we have a glare metric. So lower is better, which would lead to that star being best. And on the right-hand side, we have a solar gain metric, how much energy, solar energy is coming in. Again, high is bad, low is good. So in all cases, we would love to have an option down here at the base. So if we say, well, which is best, we're already getting into a subjective discussion, because how many units of daylight autonomy is worth 1 unit of glare? How many units of energy is worth 1 unit of daylight autonomy? You know, how can you say this is optimal if you've already embedded a subjective decision into that process? These are apples and oranges. So this is multi-objective optimization, because there is better or worse. So I can't tell you this is the best design, but I can explain why one might be better than another. So what we have here is called a Pareto front. Forgive me if I said that wrong. This gray dashed line represents all of the things that we've simulated, which I can say objectively perform better than others, because, let me show you this one here. Let's compare this upper left-hand corner. So let's say this is one option. It's suboptimal because I know that there's a solution that performs just as well on glare that has a better daylight autonomy. That's way over here on that curve. Likewise, there's one that has the same daylight autonomy and better glare. So options here are, by our 2 different metrics, worse, which means that anything that's along this line is potentially best, given these 2 metrics, if we say these metrics are what we want. And recognize there is no actual best down here, because it doesn't exist. We tested them all. That's not a realistic scenario. So first thing we did, said, all right, let's look at what these potential optimals are. And let's see what they all have. So which one has the best daylight autonomy? Now it's going to have terrible solar gain, but the best daylight autonomy. Big surprise, it's a giant glass facade, because we're just slamming this thing with light, which makes sense. Now as we start moving down, all right, we're going to give up a little bit of daylight autonomy, but we're going to gain a lot in solar gain reduction. And here you have, interestingly, all these options have the all glass. They have a very high VLT, but this one now has a some fins. As I start moving down that Pareto front, they're all the same design, with just increasing levels of fin density, with some uniqueness with the rotation versus the spacing, right? But they all were full glass and highest VLT, which is interesting, and it kind of makes sense, because you want to maximize your daylight, you want as much light coming in, but if you want to reduce the solar gain, you want to block the direct sun. So basically we have these facades that are blocked to the direct sun, but very, very open to where there isn't much direct sun, northern type sky. This is a western facade, so the openings are facing more northerly. So that makes a lot of sense. Yeah, question?
What software are you using now? Is this still Grasshopper?
Oh, thank you. This is Grasshopper. I should have clarified, yeah. The question is, what software are we using? This is all in Grasshopper. We're using the Honeybee Ladybug Tools components. And we use Calibri to generate all the options. And Design Explorer is my personal favorite sort of data viewer. And actually those graphs were created in a separate Python to get some customized visuals. But yeah, this is all with Grasshopper components. Strongly recommend you check out Honeybee if you want to do any kind of performance analysis. My favorite. Great question, thank you. So what we're finding here is that they're all basically the same design. And I mentioned before that I think that optimal is not really true. It's like anytime someone tells you optimal, it should be a red flag. Because what is not accounted for in my model here? True energy. I'm looking at peak solar gain. What about conductive heat transfer? How much energy is lost through this facade in the wintertime due to it all being glass and not being a well-insulated, say, solid wall? Probably a whole bunch, right? Is this even going to meet code? What about cost? How much does the full glass and all these fins cost? So I might say this is optimal, and the architect's going to say, well, that's cool, we're not going to do it. It's unfeasible. So this is what I mean by optimal being a fallacy, is that you probably have not accounted for everything in your model. So although data looks cool and data looks powerful, we have to remember it's only garbage in, garbage out. It's only as good as the assumptions built into your model, and very often we don't really understand the limitations of those assumptions. And I would warn architects especially. I feel like engineers are trained in school to be hyper tuned to every little detail, and that probably drives architects crazy, because you're like, it's fine, right? Like, you want to be more flexible, you want to be more loose, but you'll get tripped up when it comes to data stuff like this, because you might make assumptions that are incorrect, whereas the engineers are trained to maybe be a little more conservative or a little more risk averse. So everything on this Pareto front, the optimal ones, were not actually viable solutions. And we recognized that right off the bat. So instead we said, all right, let's try to give them recommendations. So we failed in the past. Often when we'll do studies like this, we have 10,000 things, a whole bunch of options, and we'll show it to the architect, be like, cool, you pick. And they're like, well, that's why we brought you on board. You tell me what to do, right? Or inform me. And so that exchange often gets overly complicated. You get a overwhelming, too much data, right? Too much data, and very often we just want clear design directives. Architects have more things to consider. So what we did is we went through and said, all right, for each section of facade, what would we recommend based on our experience? So the first section, where it's very, very glassy, we went through and we looked at all the possible options, and we identified actually one that happened to land on the Pareto front. We knew this was a good option, but we identified a reasonable fin depth and rotation that worked, that we'd recommend. So, okay, this is what we recommend here, and you can see it performs pretty good. In the middle here, we ended up recommending an option that had significantly less solar shading than they had originally wanted, because as you have more solid, you have less glass, and it was really the window to wall ratio that we found was driving the daylighting performance. At a certain point, if you want a lot of daylight deep into space, you just need a lot of open glass, and the more you shrink that glass, or the more you shield it with shades, the less you have. So a little bit of external shades helped protect for the peak solar gain, but if you did too much, it would begin to break down. So we chose a good middle ground for that window to wall ratio option. This was our attempt of essentially getting the cost and the full energy into effect, because we knew we couldn't go all glass, even though we weren't running an energy model. And then we chose an option where we said, all right, what if we had 30% window to wall ratio? Here we said don't put any external shades, because you need as much sunlight as you can get. And you know what? You're already doing pretty well with your peak solar gain, because half of the wall is solid. That's the best shade you could possibly do, is not have it glass at all. So we said you're already doing really great. No need to ruin your daylight anymore to get a little bit of extra solar gain reduction. Now that was exactly the opposite that the design team originally set out to do, because they originally wanted to have very thin, small fins at the glassy portion, and then get really big honking huge fins as it went down farther. And so our recommendations basically said to flip that. Now we went one step further. So what you just saw here was more of a data-driven approach, where the goal was to sit down with the design team, explain how things are working without actually analyzing their facade. We did it anyway, just because we knew they'd want it. But for the next steps, now we can have a discussion, we can understand why things are working, what we would recommend. Now they have a kit of parts they can work with. So this is now actually guiding the next steps and the steps after that, which is what we think any kind of good engineer or good consultant should be doing, trying to inform the design process. But even here we often run into trouble where it's not as visual. We showed a lot of numbers, right? It's just not quite as fun. And we think we can do even better. We have access to all this information. And so here's something we've been playing with recently to get real-time analysis built in. And it comes down to a actually pretty simple application of machine learning, which I know is so overused. It's like fancy term, AI, machine learning, right? It sounds really complicated. As we're going to show here, 2 components in Grasshopper, you're up and rolling. Machine learning could be as simple as, you guys use Excel and you have a scatter plot and you want to fit your best fit line. You guys ever done that? That's machine learning. That's not very sexy. It's not very fancy. We are essentially, in this example, doing the exact same thing. It's called regression. So think of it like a best fit line, but rather than a line through a cloud of points, it's a little more complicated. But basically what it's doing, if you have a parametric model where you say some inputs, all this stuff happens in between, now I get some outputs. Well, to use machine learning, we can do the exact same thing, but the neural network in this case will basically learn all the patterns and trends that the parametric model, including your Honeybee simulation engine, represent. Because if you've iterated through, so we said how we took that room and we generated all the possibilities, so all that data lined up. Well, it takes all that data, and what you have is a bunch of inputs and their corresponding outputs. And all machine learning does is it takes those inputs and outputs, it sucks them in, it learns from them, it identifies all the patterns. Neural networks are called universal function approximators, which is a fancy name for a best fit curve. But it's, it'll learn all the stuff. So then, if I give it new inputs, it'll predict a new output. Just like if I have a best fit curve and I give it a new point, it's going to say, well, that's the location on the line. So it's regression is what it's called. And what it allows us to do now, critically, is that notice that these are intentionally drawn to look the same because now they are. Only that parametric model, take daylighting for example, how long would it have taken to run that? 5 minutes? 5 hours? Well, running through a neural net, milliseconds. Which means now I can run this in real time. And here's the actual thing in Grasshopper. So, I mean, these are the nodes. I was using Dodo. There's a whole bunch I've been looking into recently, but it's just two things. So to train the neural network, you take a bunch of training inputs, which we call X, and then training outputs. So that's the inputs and outputs that we've collected. That's our big database. You just plug them in as a tree structure, and you click train, and it learns. It takes seconds. It's like, cool, done. And then you have another node that says, well, give me that neural network you just trained. Give me a new series of inputs. That's the new inputs, and it spits out a prediction. So that's it. It's just two components. And now, there's a lot of applications of machine learning, so I don't mean to say that all machine learning is as simple, and there's 1,000 ways you can design your neural nets to be more accurate. There's a lot of stuff you can go into it, but I think it's important for us all to not get scared by some of this stuff, because as I'm showing here, it's two components, and it can enable things like this. So, in this case, we trained it to, it's not actually analyzing this facade. Instead, what we built was, for every one of those grid points that you see, it's looking at my Grasshopper facade and it's measuring the major parameters. What's the window to wall ratio, the average fin rotation, the average, all those inputs to our neural network. It's finding out what those average inputs are for that portion of facade, then it's predicting those values. So really, all that neural net is doing is we ran every possibility, right? So essentially, it's looking at my Grasshopper facade and saying, you know what, this is closest to this option, but not, say we ran 180 options in this case. But this particular section of facade, it's in between these two. Well, I'm basically interpolating. The neural net is that best fit line, so I'm like 3/4 of the way. Boom. But it's a more complicated thing. It's 3/4 of the way between all of the points, right? It's going to be some weird spot in there. The neural net's going to figure that out, like a best fit line. So when I give it anything else in between the values I measured, it'll predict what it's going to be. And so it's not perfect, right? You still need to go afterwards and maybe validate, make sure it's right. But what does this allow us to do? I'm able to play with all of this stuff, and play is a key word here. I'm able to discover what works and what doesn't. Which of these decisions makes the biggest impact? Now, I might have an understanding because I analyze all that data, but imagine empowering your designers with a tool like this, where it's like, we could have a meeting, but you know what? Why don't you go play with this for a little bit? And here's a dashboard at the top that's giving you some of these key metrics that my analysis would give you. Now, I'm not even in the loop. And what if this daylighting engine, this neural net, could be applied to any of your future designs? Well, I no longer have to even be there. And how many hours or days would I spend reacting in vain to your erratic design decisions? I'm being a bit facetious here, right? But this is a fast-paced design process, and we must challenge our engineers to keep up, because we can. What this shows us here is that it is possible. This is what computational design can do for us. We can do better. We can do things that seemed impossible. And really, that's why we wanted to build this. And reality, full disclosure, this was still too late in our design process. And I think in the end, budget came in, and they're redesigning it anyway. So, like, regardless of all this work, something else happens. So I'm not saying that this is a cure-all, everything is solved silver bullet, but we are showing, I think, a fundamentally new capability, and that is we can inform design in ways that are vastly superior to the status quo. So I would encourage you all to go back and tell your teams to ask for more, because it's now possible. And that's what we got. Any questions? Yeah, what's up?
So, was any of this design process based off the program on the inside? Like, was there a need to have more light in certain areas, or maybe more solar gain?
Great question. So for the recording, question was any of the facade decisions driven by program on the interior? The intent was yes. They had different sections where we knew, for example, the southern portion needed more daylight, and as you got more towards the middle, it was just a shallow corridor. We didn't need as much. And had we been able to take this fully through, that's exactly where something like this could have come into play, because we could have explored more options to react to that. So that was the intent, but the way the whole process came out, we didn't actually get that far to really fine-tune it for that. But you could imagine how easy that would be to just look and to play with it. Yeah. So the question was, what were the machine learning components? I used Dodo for this particular example. Yeah, like dodo bird. I don't know, these animals. I liked it for its simplicity. I couldn't figure out how to customize the layers of the neural net, so all I could really use was the default. Now, it worked well enough. I actually ended up going back over and figured out a way to really get control over things using a custom approach, which I wouldn't recommend because it was a lot slower than theirs, but I was able to get the numbers much more closely aligned with the data. The accuracy got much closer. So there are other plugins. Crow is one that I've been meaning to look into. That gives you more control over the layers, and the layers are just sort of the architecture of the neural net, kind of adjusting your accuracy and all that. I would strongly recommend looking into Design Space Explorer, which has a variety of different components to allow you to do this process. It's one that I've really been meaning to look more into. There's a whole host of them. I'm actually working with somebody to try to sort of make a blog post about all the stuff that's out there, because we started looking and there's like maybe a dozen different plugins that all do this stuff. So it's less, I'd say, about the plugin, and I think it's more incumbent on us to understand what it's for. So when people say I use machine learning, it's like, no, wait, hold on. We're using a regressor, we're using a clustering algorithm, we're using a classifier. I think those are the terms we should start thinking about. Really, what is it doing for us? Forget which one we used. What was the end goal? I think that's going to be the approach. And then once you have that figured out, then it comes down to, well, what plugin will do that? The short answer was Dodo. Cool. All right. Well, I think that concludes this pitch. I'm going to shut off our recording. And thank you guys so much for being an attentive audience.